today's video, we're going to be looking to calculate the friction factor head drop given flow and flow given head drop in Python code. So to do that, we're going to start by listing out some of the equations that we'll be using within the code and breaking down what they mean. So first, for the friction factor, we're going to be using Churchill's. So which formula we use in this case is Churchill, is based upon the surface roughness and the Moody's diagram, which we'll show you in a second before we hop on over to the code. And so according to Churchill's formula, we have that the friction factor divided by 8 is equal to the quantity of 8 divided by Reynolds number to the 12th power plus 1 over theta 1 plus theta 2 to the 1.5 power, that entire quantity to the 12th power. And we are given that theta 1 is negative 2.457 natural log of 7 divided by Reynolds number to the power of 0.9 plus 0.27 times the epsilon. So this is where the roughness of the material comes in. And then this is d, the diameter. And then theta 2 is going to be 37,580 divided by Reynolds number to the 16th power. So Reynolds number is defined as density times the diameter times the velocity divided by the viscosity. And so that's what we're going to use for part A, which is to determine the friction factor. And then for part B, we're going to use something called the head form. So this is based off of Bernoulli's equation. So Bernoulli's equation is that pressure 2 minus pressure 1 divided by the density plus viscosity 2, velocity at the second position squared minus velocity at the first position squared divided by 2 plus gravitational acceleration times position 2 minus position 1 is equal to the negative frictional heating. And then so the velocity is not changing, and so that's going to be equal to 0. And then to get the head form, so this is Bernoulli's. So to get the head form, what we do is we divide everything by the gravitational acceleration. So that's going to give us the pressure at position 2 minus the pressure at position 1 divided by the density times the gravitational acceleration plus the position 2 minus position 1 is equal to the negative friction factor divided by the gravitational acceleration. And then so if we remember that frictional heating is equal to 4 times the friction factor times a change in x divided by diameter times the velocity squared divided by 2. This was derived in a previous equation of ours. And so the change in x is just going to be equal to the length. And so if we rearrange this, because we have the friction factor, or that's what we're looking for, and we will get that with Churchill. So we have that. So what we have to do is rearrange it for the velocity. So if we remember that flow rate is equal to velocity times area, we can rearrange it to be that velocity is equal to the flow rate times the area, and the area is just pi r squared. And because we don't have the radius, but we do have the diameter, the radius is just equal to the diameter divided by 2. So this entire quantity squared is just going to be diameter squared divided by 4. And so we'll have 4, this should be velocity is the flow rate divided by the area, and so velocity is going to be equal to the flow rate times 4 divided by the diameter squared times pi. And then using that, and using the fact that we know that with the head drop and the head form that it's the frictional heating. So now we're moving on to the flow part. So the frictional heating is negative divided by the gravitational acceleration. That's going to be equal to 4 times the friction factor times the change in position divided by diameter times velocity squared divided by 2. And so we know that velocity squared, if we're solving for this velocity, we're going to isolate it, and so it's going to be velocity squared. This entire term is also divided by gravitational acceleration. So isolating this, it's going to give us 2 times the gravitational acceleration times the diameter divided by the friction factor times the change in x. And so to get rid of the squared, we're going to get the square root. And we also have the 4 here in the denominator, or in the denominator, but we'll cancel that out with this 2 here, leaving us with just a 2 in the denominator. And then we can plug this in to this equation. So flow is the velocity, so the square root of gravitational acceleration times the diameter divided by the friction factor times the change in position times 2, and then times the area. So that's going to be 4 pi r squared. So we know that the r is just diameter over 2 squared. So bringing the square into the parentheses, that's going to give us 4 pi diameter squared divided by 4. And we will have, there is no 4 there. Area is just pi r squared, excuse me. So again, doing the same thing, that's going to give us pi times the diameter squared divided by 2. And so that's going to be for the flow. We're going to use this for the head drop, and then we're going to use this for the friction factor. So now we are ready to head on over to Python and write out the code. So now we can start writing out our code. And so first I wanted to show the Darcy friction factor formulas. So these are a bunch of the different formulas. We are using, again, Churchill, which is these equations here. When I had them on the board, this is where I pulled them from. And so this is based off the roughness of the pipes, which we use Moody's diagram for. So this is Moody's diagram. It gives the friction factor within, in comparison to the relative pipe roughness and then the Reynolds number. And so this is how we landed on the formula that we landed on. And so heading on over to Python, the first thing we want to do is, we already did it, we imported numpy as np. Numpy allows us to do different mathematical functions. And so the first thing we want to do is calculate the friction factor. So we're going to do this with Churchill's equation. So we're going to define a function so that whatever Reynolds number and roughness we put in, it will calculate the friction factor for us. So those are our 2 factors within the parentheses. So we're calling this just CH for Churchill. So ultimately we want it to return the friction factor, which is this equation here. So we'll have 8 divided by 12, 8 divided by Reynolds number to the 12th power. This plus 1 divided by theta 1 plus theta 2 this is to the 3/2 or 1.5 power. And then this entire quantity is to the 12th power. And then we are going to multiply this entire quantity. Instead of by 8, we'll be doing it by 2, because this is for Fanning's friction factor and not Darcy's. And then so we have some terms that are undefined, as it's showing us. We have theta1 that's undefined. So theta1 is, we were given that it is equal to negative 2.457 times the log, so np.log of 7 divided by Reynolds number, and this is to the 0.9 power, and then this quantity plus 0.27 times the roughness, and then this entire quantity is to the 16th power. And then theta2 is 37,580 divided by Reynolds number to the 16th power. And I'm adding a decimal point between a lot of the numbers so that they are not recognized, or so that they are recognized correctly by Python. And so we can shift enter. So while we're at it, before we continue, we should define a few just constants. So gravitational acceleration is 9.81, and then we have the viscosity, so rho, that's going to be 1 times 10 to the third, and then we have the viscosity mu, which is going to be 1 times 10 to the negative third. So now that we have the friction factor function, we will need to define a function for the head drop. And so for the head drop, we will need flow, the length, the diameter, and the roughness of the material. And this comes from this equation here. And so we need the flow because of the velocity, and then the length, the diameter, and the roughness all go into the actual formula as well as the friction factor. And so first, we want it to return to us this final equation down here. And so we want it to return 2 times the friction factor times the length times the velocity squared and this is divided by gravitational acceleration times the diameter. And then so a few things we don't have defined are the velocity. So the velocity is equal to 4 times the flow divided by diameter squared. So 4 times the flow rate divided by diameter squared times pi. And then we have the friction factor, which is the Churchill function that we defined earlier with Reynolds number and the roughness of the pipes. And so Reynolds number, I wrote it over here, is defined as the viscosity, or excuse me, the density times the diameter times the velocity divided by the viscosity. Yeah. So if we shift enter, that should work. So if we enter in some test values, so we can use 0.1 for the flow rate, we can use 10 for the length, 0.1 for the diameter, and let's just say 5 times 10 to the negative third for the roughness of the pipes. So that gives us, something is wrong within these, so it should have given us a number. You can see I got 0, which is not correct, and the error is that up here when we were writing out or inputting the equations for Churchill, it is this entire quantity to the 1/12th power, and so this should be to the 1/12th power, which is also incorrectly written on my board when I copied it originally. So that's our issue here. So if we do this to the 1/12th power, then it'll be this entire quantity. So I added in to the 1/12th power, but I mistakenly had already written to the 12th power earlier in my original formula because I had copied it on the board incorrectly. So if we make this change, hopefully this will fix our issue. Perfect. Okay, so now we have a head drop of 25.18, so that's our head drop. So moving on, we want to define a function for our flow. Let's just do it. Okay, so earlier we had written out these equations, and so we didn't do this with the consideration, before we code the flow rate, is the consideration that when we want when we're looking for the flow, it's going to be the flow rate that we calculated from here minus this is going to, minus the actual flow rate is going to equal 0. That's how we're going to get the flow from the head drop. And so if we were to define that as an arbitrary term as beta, we would have to incorporate this into our equation here, and then ultimately here. And so what we're going to do is we're going to end up using the root solver, and the root solver in Python will allow us to code this out and solve for at what point the flow needs to be for the two head drops, or the two flow rates, to equal to 0. So let's head on over to Python. It'll make a little more sense so we type it out within the code. We have this defined flow rate here. This is going to be our next function. And so what we're going to need is the b value, so beta. It's just an arbitrary value, or an arbitrary naming of it. And then the length, the diameter, and then the roughness. Oh, excuse me. Did not mean to do that. Okay. Oh, did not mean to do it again. Okay. And so we need to define a function within this function because we're solving for when this first equation here is equal minus the actual flow rate is equal to 0. So we're going to define this as just the flow rate, and it's going to be of a vector and so we just want it to equal the first index of the vector, and then it's going to return to us this equation that we have here. So it's the square root of the gravitational acceleration times the diameter times the b value that we give, divided by the friction factor times the change in x, which is just the length, times 2. So I want the square root of that entire value. And then multiplied by, this is the area, so pi times the diameter squared divided by, that should be a 4 because we squared diameter over 2. My mistake. So divided by 4. And then because it's an array, we have to make sure that we have brackets around it. My apologies. This entire equation is actually the guess. So the guess we have for the flow rate based upon the formulas that we had derived. And then what goes within the second equation is the fact that we have the beta value, which is the head drop, the actual head drop minus the head drop that is based on the flow that we're trying to find, minus the head drop that we calculate. So that's where our head drop function from up here comes in. And then we would also need to provide an initial guess for the friction factor, so we'll just say 0.01. And so this is where we use the root solver. So to use our root solver, we will actually need to import from SciPy .optimize. We're going to import root. And then, so now we can actually use the root solver. So we're going to use the root solver of, just to avoid confusion, we'll just change this to equation because we have a lot of Q's going on. So the equation using the guess, again, it's a vector, so we'll want to have brackets. So that's it. When we're using the root solver, we need the guess as well as the function that we're using. So that's the equation and then the QG, which is the guess that we have up here. And then when it outputs it, we just want the solution, which is x, and then the first index of that solution. And so now if we were to put in our head drop that we calculated earlier, and then the same values for the length, the diameter, and the roughness, it should, this should be FG, which is our initial guess, give us 0.1, so we got 0.9999, which is very close to 0.1, which is the flow that we put in, the flow rate that we put in earlier. So that is our code for the friction factor, the head drop, and the flow rate.